Hello and welcome to this talk about the computational characterization of surface entropies of two-dimensional subshifts. I will first introduce the notion of subshifts and try to motivate it a bit. So, consider your usual jigsaw puzzles, but we make them infinite. You have finitely many kinds of jigsaw pieces, but an infinite number of pieces of each kind. At each position in the discrete plane Z2, you have a jigsaw piece, and two pieces can be next to one another if and only if their common borders match here. Now we put this definition into a more mathematical and abstract statement. Consider first of all a set of colors, say sigma. In the case of jigsaw puzzles, sigma is exactly the set of the different kinds of jigsaw pieces. Then we define a two-dimensional subshift as the set of colorings of the plane Z2 with colors sigma that do not contain some family of forbidden patterns F. In the case of jigsaw puzzles, F will exactly be the patterns in which two pieces have a common border that does not match. And this defines a subshift being the set of all the colorings that do not contain any forbidden pattern in F, for F a family of forbidden patterns. Let's take an example. Take two colors, red and blue, and an empty family of forbidden patterns. Then every coloring of the plane is allowed, and in fact an empty family of forbidden patterns defines a subshift composed of all the colorings of the plane. So you can have this coloring, you can also have this one, etc. Now if we change the family of forbidden patterns, for example we take these three, then this coloring here is no longer allowed. And what are the colorings you can have with these patterns? You can get this kind of colorings. Of course, two families of forbidden patterns can define the same subshift. For example, if you take this family of three forbidden patterns and this one, you obtain the same subshift because there is a redundancy between this pattern and this pattern. So, let's take this family, and where does the terminology subshift comes from? Because we defined our subshifts in terms of forbidden patterns, if you translate valid coloring, the translated coloring still does not contain any forbidden pattern either. So subshifts are shift invariants in the sense that if a coloring is valid, a translated version of this coloring is also valid. For example, you can translate it by a single line, as I just did. Or you can translate it infinitely and get full red, or translate it infinitely below and obtain blue. You can have both. So all of these are still valid colorings of the plane for this family of forbidden pattern here. My main motivation to work on subshifts comes from the fact that they are a computational model. For example, consider the following space-time diagram of a Turing machine. To recall this briefly, each line of the diagram corresponds to a configuration of the machine. You have here the tape which is written, and here you say that the head is here on the tape, and with colors you encode the state the machine is in, etc. And as you go up in the diagram, the next line is the configuration of the machine as the next step of computation. You can easily encode this into a subshift and you have very little to do. You encode in your colors the different writings on the tape, so 0 or 1, colors for the state and the position of the head here or here, and as Turing machines choose their next state and position by reading a single cell of the tape, and as they can only move one cell left or right, the local rules which govern the behavior of the machine can be translated into local rules for the subshift. This means that subshifts can contain arbitrary computations of Turing machines, so, in a sense, you have some kind of computational powers with these objects. Now, finally, to conclude on subshifts, I introduce a classification. We say that a subshift is of finite type if it can be defined by a finite family of forbidden patterns. For example, think about jigsaw puzzles. And we say that a subshift is effective if it can be defined by a recursively enumerable family of forbidden patterns. Of course, if you are of finite type, then you are effective. What is interesting is that the converse holds, in a sense. If you take a one-dimensional effective subshift, then there exists a two-dimensional SFT which simulates it. I will come back to this notion of simulation later, but I want you to remember this. We can simulate effective subshifts by adding a dimension. And this will be the main method we will use in this presentation. Now, before talking about surface entropies, I have to talk about topological entropies. Indeed, topological entropy is easier to understand, and we will later use methods for surface entropies which are similar to the ones I am about to introduce for topological entropies. And before talking about topological entropy, I have to introduce the complexity function. It is a very combinatorial notion which counts the number of patterns of size n times n which appear in the subshift you consider. So you have a set of colorings, and you count the number of different patterns which appear in it. For example, take this configuration, this coloring. Then I claim that there were exactly 5 different patterns of size 2 times 2, blue and yellow, blue and red, blue and blue, yellow and blue, and red and blue. And there are no other ones. This is exactly the idea of the complexity function. You count the number of different patterns of a given size that appear in your colorings. Now I want to provide some intuition about the complexity function, so I want you to think of it as a notion of density. Indeed, take a coloring like this, with black and white squares. And now, for each white square, I will duplicate it into 2 kinds of white squares, some with 1s and some with 0s. This is what I call adding 3 bits to the white squares. So, for each white square, it can have 2 values, 0s and 1s. Now, what is the value of the complexity function? You have to think of it as, if you consider this square, it can be 0, or it can be 1 here. And this is also true for the square next to it. So, if you have 0 here, or you can have 1. And same is true for here. So basically, if you take 2 white squares, you get 2 times 2 equals 4 possible patterns. And now, if you take patterns of size n times n, what matters is the number of white squares inside it. In fact, the complexity function is 2 to the power of the number of white squares, roughly. So the idea of the complexity function is that by controlling the density of white squares in this kind of construction, you control the value of the complexity function. And we will heavily rely on this method later. Now, let me talk about topological entropy. Computing the exact value of the complexity function can be quite cumbersome. So the topological entropy is a way to only consider its asymptotic growth. It is easier to compute the coefficient in front of the n square here, rather than the whole and exact complexity function. And this is what we call the topological entropy. And the question I want to ask in this section is, what are the possible values for the topological entropies of subshifts of finite type? In fact, this question was answered in 2010 by Orman and Meyerowicz, who surprisingly proved that topological entropies were exactly the right computable real numbers. It is a surprising result. Indeed, the entropy is a very combinatorial notion. Subshifts are defined by forbidden patterns, and the complexity function is defined in terms of valid patterns. Yet, the characterization they provided is a computational one. If you don't remember, a real number is said to be right computable if there exists a computable and decreasing family of rational which converges towards it. So, this proof is in 2 parts. First, if you take an SFT, we prove that the entropy of the SFT is right computable. First of all, I have to mention that the complexity function is not computable. Indeed, it was proved a long time ago that the emptiness of a subshift is undecidable. And of course, the complexity function is equal to 0 if and only if the subshift is empty, so you can't hope to compute the complexity function here. However, you can decide to count the number of patterns of size n times n which contain no forbidden patterns. The difference between these 2 points lies in the locality. The first point counts valid patterns in whole colorings of the plane, while the second one only looks at finite patterns. Not all locally admissible patterns, so patterns which do not contain forbidden patterns, are globally valid. So in the second point you may count more patterns than you should do. However, for some topological reasons, the second thing you count catches up with the first one at infinity, and the limit of this quantity, the infimum of this quantity, converges towards the topological entropy. So all in all, the topological entropy can be written as the infimum of a computable sequence, and as such, it is a computable real number. Now, consider the converse. For every right computable real number h, we create a subshift of finite type x, whose topological entropy is exactly h. This is the hard and most interesting direction of the proof, and the one that requires some creativity. So how can we do that? Recall that complexity function is really similar to density. So what we want to do is that we want to set the right density of white squares, and this right density should be the real number h. For example, take h be equal to this one, and look at the binary decomposition of x. The first bit of h weighs half of its total value. The second bit of h corresponds to 1/4 of the total value of h. The third, 1/8. The fourth, 1/16, etc., etc. So, consider the first bit of h. It weighs 1/2, and because it is 1, we decide that 1 square out of 2 in this line should be white. Now consider the second bit of h. It weighs 1/4, and because it is 0, we set 1 color out of 2 in this line to be gray. Consider the third bit. We set 1 color out of 8 in this sequence to be white. Consider the fourth one. We set it to be black. The fifth one, we set it to be black, etc. If you do this to infinity, we obtain a line whose density of white squares is exactly h by construction. And this is an effective subshift. Why? Recall that h is right computable. You have an enumeration of rational numbers which decreases towards h. So in parallel of this enumeration of rationals, you can forbid patterns whose density of white squares is too high in regards to the lowest enumerated rational yet. And at infinity, the density of white squares converges towards h. So this is an effective one-dimensional subshift. Recall that you can simulate effective one-dimensional subshift by subshift of finite type in 2 dimensions, according to this theorem. The idea is that you take a line, it is effective, you repeat it vertically, and with some construction lines and embedded computations, you can make it an SFT. And again, I apply the idea of density. On the white squares, I will add 3 bits. And now, to compute the complexity function and the entropy of this thing, recall that we want to create an SFT whose entropy is h. We have to count the number of white squares in a pattern of size n times n. And you can observe that because the density of white squares in a line is h, there are n times n squared different patterns of size n times n. And all in all, this proves that the topological entropy of the subshift is exactly h. To sum things up, in the previous slides, we proved that the entropy of 2-dimensional subshifts were exactly the right computable real numbers. And the main and important aspect is that, by using a theorem of simulation between different dimensions, we proved that for any right computable real number, there exists an SFT with the same entropy. Let me now introduce the main object of my talk, surface entropies. In the previous proof, I talked about why computable real numbers as infimum of decreasing sequences of rationals. Here. There exists an analogous class of left computables, defined as supremum of increasing sequences of rationals. You can then define sigma 2 real numbers, which are supremum of right computable real numbers, so you get a sequence of rationals which decreases, but you can consider the supremum of the infimums, so there are two senses, in a sense, decreasing rationals and supremum of infimums. And of course you can define pi2 real numbers, which are infimum of left computable. In fact, there exists a whole hierarchy of alternating infimum and supremum to define increasingly bigger classes of real numbers. Right computable real numbers, or bar1 real numbers, were used in the case of topological entropies. For surface entropies, a similar result will require us to go a bit higher in the hierarchy. Now, what is the surface entropy? As we already mentioned, for two-dimensional subshifts, the complexity function can grow at most quadratically, here. And the entropy is the quadratic coefficient here. But what are the other possible values of its asymptotic growth? I mean, what are the different possible values of alpha here, such that the complexity function can grow in this way? Meyerowitz answered in 2011 that any pi3 real number, between 0 and 2, can be an asymptotic growth, that is, can be an exponent in this expression. So, what happens if the complexity function grows linearly? In other words, if the coefficient, the exponent here, is 1. This is the idea behind Denis Pace's thesis in 2018, in which he introduced the surface entropy of a subshift, that is, the coefficient in front of the linear term of the complexity function. In our paper, we ask the very same question as Horman and Meyerowitz asked for topological entropy. Here we ask what are the possible values of surface entropies for subshifts of finite type. Here, we will prove that surface entropies are exactly the class of pi3 real numbers, using the characterization of pi3 real numbers just above. Pi3 real numbers can be written as lim-sup of right computable real numbers. There are two directions in this proof. First, we have to prove that surface entropies are pi3 real numbers. So if we take an SFT, we can prove that the surface entropy is a pi3 real number. If you know a bit about the hierarchy of real numbers, this is relatively easy. The converse is, once again, the most interesting part of this proof. Given any pi3 real number h prime, we want to create an SFT x such that the surface entropy of x is exactly h prime. How can we do that? Recall that topological entropies are about quadratic growth. So we studied a line, repeated it vertically, and studied its density. Here, we want a linear growth, not a quadratic one. So we have to be more creative. What we do is that we specify the construction of topological entropy. So here are the positions we used in topological entropy, and what we do is that these points, we move them apart from one another, so that in this square of size 16 by 16, there are exactly 16 points. So this contributes linearly to the complexity function. And then, exactly as we did for topological entropy, we use a controlled density of right squares to obtain, locally, inside this square of size 16 by 16, the right density. And then, we make these locally right squares sit next to one another. The density of right points in the square of index n is said to be exactly the nth right computable real number of the sequence whose lim-sup is the pi3 real number h prime. If the squares do not interfere too much, the biggest square will become dominant, and the locally right surface entropy will become globally the right one. In fact, we can prove with some cumbersome computations that the surface entropy of this construction is exactly H prime. And what is interesting is that this construction is a subshift of finite type. Indeed, if you look at the line on which all the squares sit, here, this is a one-dimensional effective subshift. So you can repeat it vertically, and with some additional construction lines, you can obtain this kind of colorings. And so you can obtain the right surface entropy. In this figure, I hid the construction lines, but you can roughly consider this kind of configurations to be of finite type, defined by finitely many forbidden patterns. So now, let me conclude. I asked the following question. Imagine you have a two-dimensional subshift of finite type whose complexity function grows linearly. What are the possible values for this coefficient for its surface entropy? And the answer is this one. Surface entropies of these subshifts of finite type are exactly the lim-sup of right computable real numbers. Indeed, if you have this coefficient, it is a pi3 real numbers, and you can realize any pi3 real number as the surface entropy of some subshift of finite type. Now the take-home message. What I want you to remember is the definition of subshifts, which are sets of colorings of the plane defined by forbidden patterns. And the second thing is that these subshifts, which are both dynamical systems and computation models, have parameters which do have a computational characterization. In particular, in this talk, we explored the previous result on topological entropy and used similar methods to study surface entropies, the linear term in the complexity function. I now want to thank Pascal Vanier for his supervision while we did this work together, and I want to express my gratitude to you for your attention. Of course, if you have any question, or if you just want to come and say hi, please join me for the dedicated session and ask. Thank you very much.